In this lecture, I'm going to introduce us to topics related to Chapter 6. So Chapter 6 focuses on transition metal mediated reactions. Okay, and this is a fine title, but mediated could be kind of the transition metals could also be catalyzed, I'll just say, or could also be catalysts for the reactions that are catalyzed by the transition metals. Okay, so there's a few ways to sort of look at this, but most often we'll spend time with catalysis. But this is an important branch of organometallic chemistry. I'm going to say an important branch of organic chemistry too. So organic and organometallic chemistry. If you've taken descriptive, there might be a bit of overlap, but let's kind of discuss some of the organometallics that we've seen already. You know, in this class and in other classes, there's R lithium. I know it's not a transition metal. And I'm going to abbreviate transition metals as TM for a while. And so transition means between kind of the main blocks of the periodic table, that bridge from the first two groups to the back, you know, the other 3 through 8, as we typically would say. There's that sort of kind of bridge between the two. Those are the transition metals. So lithium would not be one. But I like to remind us that we've been studying metal-mediated reactions. So our organolithiums and our organomagnesium compounds, these are nice starting points, even though they're not transition metals. So both of these are not transition metals, but both have been used as good nucleophiles and bases. And that's sort of to prime us for when we actually do look at our organometallic compounds. And so one that we saw actually in organic chemistry too was the Gilman reagents. These are sort of, these are like Grignard reagents. But with copper. Okay, that we would say they were R2CuLi. And so Cu, now we have copper, which is Cu, and hooray, that's a transition metal. Now, another way of thinking about these was having R groups attached to the Cu. Then the Cu would be overall -1 charged. And so that would then be countered by a lithium plus. So the lithium is sort of a counter ion here. It's a counter ion to the copper complex. But this is now another version of R minus. R minus, like our good nucleophiles and bases, the R minus is from the Grignard reagents and the organolithiums. Okay, sorry, I just went off screen there. I'm going to just take this out a little bit so I can keep going. So with that in mind, we can start to think about how these things actually sort of work. I mean, a good starting place is to think when R is attached to a metal, where R is some sort of carbon species, we have a delta plus on the R and a delta minus. Oh gosh, excuse me. A delta minus on the carbon and a delta plus on the metal. Sorry about that. Missed the whole point. Okay, so delta minus on the R group and delta plus on the metal, that is, the metal is much more electropositive than the carbon. And what I've tried to kind of hint at is that it's helpful to think about R minus being countered by some metal. But the equilibrium of this sort of covalent bond with the metal to an ionic bond sort of depends upon the metal that's actually being used. Okay, so what's cool about metal mediated and metal catalyzed reactions is that you start to get to some different reactivities. So I want to just remind us of some possible scenarios for when we take our R metal and we react it with an alpha beta unsaturated carbonyl, like a cyclohexenone. So let's go ahead and take cyclohexenone, and we're going to react it with R attached to some metal. And what I want to do is think about R minus engaging this molecule. Now there's a few ways to look at it. We could have the typical resonance structure of a carbonyl where we have a negative charge on the oxygen atom and a positive charge on the carbon atom. That's actually that actually could be further drawn as an enolate resonance structure with a positive charge at the beta position. So now we have an R minus that can attack the carbonyl carbon or the beta carbon. We call the carbonyl carbon the one addition to the carbonyl carbon, this first resonance structure, as our 1,2 addition product. And then when we add to the beta position, it's our 1,4 addition product. And the 1,4 addition product would be like the what's called Michael reaction from organic chemistry 2. Now, so what could happen is we could get then two products. If we add our R minus, we could get our 1,2 product shown here plus our 1,4 product shown here. Okay, so we have two modes of addition giving rise to two, I guess, alkoxide intermediates that could react with H plus in a couple of ways. And what we notice, and I'll go ahead and draw that. So if we react, let's go ahead and just be helpful. So if we have our alkoxide and we react it with H plus, in this case, the O minus just grabs the H plus, negative to positive, neutralizing our molecule to give rise to an alcohol. In contrast, what happens is we could certainly draw the O minus of our enolate, grabbing the H plus, but it would just undergo tautomerization. So I'm just going to show resonance, reaching out and grabbing the H plus at the alpha position of our forming carbonyl to give rise to this species. It's not technically 1,4 unless you add the H to the oxygen and then tautomerize it, but let's just save a step. So we again have our 1,2 product and our 1,4 products. Okay, now there's a pretty cool experiment that you can do. You can take an alpha beta unsaturated carbonyl and add to it a few different metallic agents. So let's take a carbonyl and we're going to add an organolithium to it. If we do that, the outcome, and let's go ahead and then follow with H plus, the outcome is as follows. For the most part, when you add an organolithium, you get 1,2 addition. I'm going to write mostly. Part of me wants to write only 1,2 addition, but I don't think that's the case. It's mostly 1,2 addition. Now that's in contrast to if we go to our old favorite, the Grignard reagent. Everybody likes the Grignard reagent because it doesn't ignite in the presence of moisture. It's much safer to handle, that sort of thing. If you use a Grignard reagent for this reaction though, you actually get a mixture of 1,2 and 1,4 addition products. So you'd get your 1,2 addition plus your 1,4 addition products. Now, what's interesting about using a transition metal, that's kind of the goal of this chapter, like if we use copper, we actually get a different outcome altogether. Well, a different outcome from, yeah, sure enough, a good enough outcome. With our copper reagent, our Gilman reagent, we'll selectively only get the 1,4 addition product. So it actually diverges from both of the previous examples somewhat. And this is another depiction of a Gilman reagent. If you just write R2CuLi, that's fine as well. But if we have copper present, now we're going to exclusively get 1,4 addition with high selectivity. So the transition metal actually allows us to kind of switch our selectivity and give different products in high yield. If we, another way of getting this 1,4 addition product would have been to, use the Grignard, do the Grignard reaction and then get it in low yields, as it would be then a mixture of products. Okay, so what we have to do when studying transition metal mediated reactions is we need to shift the focus. So in transition metal mediated, as is the case above, or we're actually going to spend a lot of time with catalyzed reactions, we want to shift our focus towards the metal involved. And we're going to ask questions like, for this metal, what's going on with its valence electrons? Okay. Now what we get is kind of an opportunity to introduce new things bonded to the metal. It's not really new things that can bond. I'm just going to write different things. So different things can bond to metals, and the bonds can be ionic, covalent as a sigma bonds, and covalent as pi bonds. So we really get the entire bonding arsenal to many of these transition metals that we're going to study. So for example, we could have a palladium complex. This is our transition metal. And the transition metal could be bonded to P, which is attached to 3 phenyl groups. So P again is phosphorus. So we show a bond to the phosphorus atoms. So it's a 2-electron sigma bond to phosphorus. But then we could also bond with the pi bond of a double bonded system. So I'm going to draw a line over to an alkene. That is something with a double bond between 2 CH2s. And I'm going to be very careful about my drawing just this first time. But I'm going to have the line from the palladium to the ethene. I'm going to have it just kind of bump right up into the electrons that are bonded between the 2 carbon atoms. So we have a carbon-carbon double bond, and it's that bond that actually supplies 2 electrons from the pi bond. Okay? So what we say then is palladium is attached to a bunch of non-metal atoms. It's actually attached to 4 non-metal atoms. And how is it attached? It is attached to 2 times phosphorus and 2 times carbon. Now the carbon one is kind of interesting because up here palladium forms a complex with the pi electrons on both carbons. And so we say that it's simultaneously attached to 4 non-metal atoms, 2 palladium and 2 carbon atoms. Now, what's sort of interesting about this is I don't really care about the number of elements attached. Instead, I want to focus on how many electrons does each atom provide. And because these atoms, because these things that are attached to the transition metal could be atoms or even bonds, I want to replace, I want to be a little bit more general as to the type of things that can attach to my transition metal. I'm going to cross out the word atom over here. I'm going to cross it out in red so you can see it. I'm going to cross out atom and I'm going to replace it with a better word, which is ligand. Ligand. Some people call it ligand. I don't really know. So instead of focusing on the atoms that are attached to the transition metal, I want to focus on the electrons available to the metal, the transition metal, from the ligands. So I want to focus on the electrons from actually electrons on the metal from its ligands. Okay, and it's this that actually controls these electrons, really determine the properties of the transition metal. Now that's pretty cool because that suggests that a transition metal can actually have vastly different properties from another, a transition metal in a complex could have vastly different properties than the same transition metal, the same palladium type of element, as long as it has different ligands attached to it. In other words, so the transition metal could behave differently if it has different ligands attached. Okay. In this case, if you've got P, and then I'm going to write just pH3 over here like this, and that's attached to palladium, pH3 like this, and then we have our pi complex to an ethene, we actually get a grand total of 6 electrons from the ligands. Now, I don't want to spend too much time on this. We will revisit in a later lecture. But the fact that we have 6 electrons from the ligands means that this complex is going to behave differently than if we had 4 phosphorus ligands attached to our palladium. For example, if we had palladium attached to PPH3 here, PPH3 here, PPH3, and it's the phosphorus that's the attaching atom. It's just on that phosphorus we have 3 phenyl groups around it. We would say that in this case we actually get 8 electrons from the ligands. And again, don't worry about where I'm getting the 6 and the 8. Just worry that the metal complexes are different and the electrons from the ligands are different. Now, before we move into, and I think counting electrons around the transition metals is some of the more important things we'll get from this unit. Before we get into that, let's just look at some conventions. So conventions when studying transition metal mediated, or actually just transition metal complexes. Okay, the one that took me a little while to wrap my head around was there are no formal charges used. Okay, so for example, if we had, let's say we have palladium 2+, it's in the +2 oxidation state, and that +2 indicates, you know, you could see a plus and a minus between the PPH3, which we've seen is a pretty good ligand. We could have those interact. Now, typically, if we had some sort of electrophile, just general electrophile, and we let the PPH3 react with it, we would get electrophile being neutral, and then PPH3, phosphorus is in the same group of the periodic table as nitrogen. We put a plus charge on the phosphorus, and then we would neutralize the +1 oxidate, or the +1 charge of the electrophile in this case. This is not what we do for transition metals, okay? That may work with like a carbon-based electrophile, but what we do with transition metals is we write palladium 2+ bonded to PPH3, no formal charge. So now, even though the palladium, or excuse me, even though the triphenylphosphine, the phosphorus with 3 phenyl groups around it, now has 4 sigma bonds, we don't write any formal charges on it. We just keep it as is, which includes the +2 oxidation state. And we just write the PPH3 bonded, and we just kind of get used to it. Notice I didn't decrease the charge on palladium by 1, which is what I did with the generic electrophile. Instead, I just wrote palladium 2+. Still, it's as if the oxidation state was not affected. Okay, now what we have to do is we need to be careful when we let ligands bond to our metals, when we let our non-metal atoms of our ligands bond to our metals at all. So, okay, so far you're like, okay, I guess I can get used to it. The palladium +2 keeps its oxidation state, and you just draw a line between it and the triphenylphosphine ligand. But what if we have palladium 2+ reacting with a Cl-? Cl- is also often seen as a ligand. We really want to draw curly arrows, right? We really want to draw curly arrows to show the formation of palladium chloride. And then let's just have the palladium neutral and the palladium now at a plus charge and the chlorine neutral. But that again is wrong because we don't use formal charges. We draw oxidation states. So draw oxidation states. Actually, that's correct, I should say. Gosh, shoot, sorry. That is correct. Draw oxidation states, not formal charges. So I was about to redraw that and be like, look, you don't draw the chlorine with a charge. Well, yeah, the chlorine doesn't have a charge. So what we have to consider when we're doing this is there's not like a really good kind of common set of rules for just drawing these complexes. I say that and then I'm like, well, I'm thinking through all the rules. Well, the rules just don't really jive with what we do with main group atoms like chlorine, or carbon, phosphorus, chlorine, those sorts of things. As soon as we introduce transition metals, we have to kind of follow a new set of rules. Let's just immediately move into some more kind of different ways of thinking about this. Okay, so let me just first of all cover what we need to know about our transition metal complexes. These are things we should be able to do. Number one, we need to be able to determine the total electron count on or of the metal. Number two, we should be able to determine the oxidation state of the metal. I guess B. Determine the oxidation state of the metal. And then C, we want to determine the d electron count of the metal. Okay, so what we'll do is we'll spend some time looking at how to determine each of these things. So something that's really helpful for getting into this is to look at what's called the 18 electron rule. And so the 18 electron rule is kind of like the octet rule, but for transition metals. Okay, so the 18 electron rule, we'll touch on this before we break for this lecture. The 18 electron rule says that thermodynamically stable transition metal complexes tend to have 18 electrons in their valence shell. Now, as I indicated, this is like a transition metals octet rule, except instead of 8 for the octet rule, we have 10, an extra 10 electrons from the d orbitals. So said another way, if you recall, for each shell around a nucleus, and these are the shells that we put our orbitals in, for each shell around a nucleus, beyond the second shell, we have 1 times an s orbital. So the s orbital can hold 2 electrons. We actually have 3 p orbitals, all orthogonal to each other, px, py, and pz. So we have 3 of those. If we have 3 orbitals, we can hold 6 electrons total. So 2 plus 6, there is our 8 electrons of the octet. Now what we can do additionally is consider our 5 d orbitals. If you've taken descriptive, you know these have some interesting shapes, but now 5 times 2 is 10 electrons. So we get 8 plus 10 equals 18 electrons. And because our transition metals are all beyond row 3, they actually do take advantage of their d orbitals quite a bit, allowing us to get up to 18 electrons to fill a shell. Okay, so it turns out though that the 18 electron rule is helpful for determining if a complex is stable. So this is true, but ... the 18 electron rule is more easily violated than the octet rule. So you can break the 18 electron rule, and you do so pretty easily just by like having stuff randomly fall off. And so you don't always kind of go over the 18 electron rule. I can't think of really any example off the top of my head, though I'm sure some exist. But by violate, I mean you fall short or have less than 18 electrons. So that's common. It's common to have less than 18 electrons, much more common than it is to have less than 8 electrons for a typical main group. And the reason why is, we could ask that, we could write that specifically. Why does the 18 electron rule get broken? Okay, so why does the 18 electron rule get broken? Well, there's a lot of deep arguments as to why, but generally, we just could say that the valence shell that we're filling up to 18 electrons is far from the nucleus. It's far from the nucleus compared to the first and second shell. So it's farther away if we're in a row 3 element than it's the third shell. You know, you keep going down the periodic table, you get further and further away from the nucleus. It's easier to break those rules, be off by a charge, countering the nuclear charge. Now, the other thing that's important to realize is that with the octet rule, we could kind of fit 4 things around a carbon atom to hit its octet, but fitting enough ligands on a metal to get to 18 electrons can be difficult. So it can be hard. So what we need to do is figure out how to determine how many electrons are on the transition metal, and then compare that number to 18 to see how close we are to a thermodynamically stable metal complex. So using the 18 electron rule is fairly simple. You just it just takes a little bit of practice to get good at counting where all the electrons come from. But using the 18 electron rule means what we have to do is count the number of valence electrons in the complex. Now this, in that list of things I said, where I said total electron count, oxidation state, and d-electron count, this is the total electron count, the total number of valence electrons. So there's my total electron count, which is again the number of valence electrons in the complex. And what we do is we compare the total electron count to the number 18. Okay, so we compare it to 18, and then if it's less than 18, we're not yet to like a fully stable complex. If less than 18 electrons, we probably have a reactive transition metal complex. Now I could write unstable out here. Now the thing that I want to emphasize here is if we compare that, this isn't like the final molecule. We're used to so often drawing the final product of a reaction, you know, proposing a mechanism and that sort of thing. The transition metal complex is what's achieving the reactivity. So we're shifting our focus to that thing that's causing a reaction to occur, which means we want it to do reactions. If it's a stable metal complex, we're not going to see reactions. If it's a stable metal complex, it's just going to sit there and gather dust as a really expensive, like, whatever. I mean, it's not doing anything. So this is good. We actually want this. I would write a smiley face here, but that implies that it's stable. So thumbs up. This is good. I don't think I could draw a thumb being up, but this is what we want. We want to actually fall short of the 18 electron rule for the most part, because then we get to something that can do some chemistry, which is what we want to study, right? Now, if we're equal 18 electrons, then we have an unreactive and stable complex. Now that's not good. That means that when we propose a mechanism and we're starting with an 18 electron complex, we probably have to accidentally like lose a ligand to get down to 16 electrons or something. And if we're down to 16 electrons, hey, we're short of 18. We can do reactions again, and it's great. So this is kind of something to indicate. What we'll do in upcoming lectures is we're going to actually practice counting the total number of electrons. And again, that's probably one of the most important aspects of this unit, this chapter 6 unit. So, hopefully you get a lot out of it. But yeah, anyway, just to emphasize again, the 18 electron rule is great, but it's actually kind of meant to be broken a little bit. So, it's not like a goal to get to 18 electrons. It's just a goal to accurately count how many electrons a transition metal has. And then from there, we can actually, see if things are reactive or not. Okay, that'll do it for this lecture.